Let's start our morning session. It's my pleasure to introduce Jens Marklof from the University of Bristol. He will speak about kinetic transport in crystals, polycrystals, and quasicrystals.
Thank you. It's a real great pleasure to be here, and I thank Alex and Leonid for allowing me to spend 6 months here at the Newton Institute. This talk is based on joint work with Andreas Strömbergsson and Balin Toth. And what I would like to talk about is an old problem that goes back to Boltzmann's original ideas of how can we derive macroscopic transport equations from the underlying classical Newtonian dynamics. And part of the reason why I'm at this program is I would like to understand what I'm going to talk about here in the setting of wave equations or Schrödinger equations, okay? And I've been talking, had lots of lovely discussions already. But this will be really in the setting of classical mechanics. We will see some partial differential or partial differential integral equation appearing, but this is really within the sort of the non-quantum setting. Okay, so here is the setup. This is the so-called Lorentz gas, which was proposed by Henrik Lorentz in 1904 as a model for electron transport in metals. Of course, this was pre-quantum mechanics, so what he did is he simply said, I'm going to model the metal, my matter, by fixed atoms, if you like, or ions that are sitting on fixed locations, and he just modeled those by hard spheres, as in the Boltzmann gas. But the distinction of the Boltzmann gas is that these spheres are not moving anymore, but instead you think of the electron as a non-interacting particle gas that moves in these fixed scatterers. Okay, so here you see our one-particle dynamics. Since the electrons are not interacting, it's an effective one-particle dynamics, which of course simplifies the problem dramatically as opposed to the Boltzmann gas. And you would like to understand the dynamics of these particles. And the Lorentz gas, of course, has been one of the key fundamental models in dynamical systems and in statistical mechanics, with the famous work starting by Sinai Bonimovic. So now the general setup is the following. So we first fix the locations of our scatterers. This will be some point set P. The scatterers will all have the same radius, and you can think of them as just hard sphere scatterers. I'll actually allow also smooth potentials. I'll specify this in a second. Particles are non-interacting, and we are moving with constant speed. This means between collisions. So this just means that there are no external fields. Okay, so we just move with constant fields along straight lines. Then we hit something, we reflect, and we move on. So the simplest possible setting. Scattering is assumed to be elastic. So from now on, we can assume that the speed is just fixed to be 1. And we assume also some homogeneity in our scattering configuration. That means if I count the number of scatterers in a big ball, that should be roughly the volume of the ball. Okay, so I don't want to have that sort of global density fluctuations. One could handle this too, of course, but it all just complicates the things, and this is already difficult enough. So here are a few examples of scatterer configurations. The first one is you take a realization of a Poisson point process. You fix that realization and you put your scatterers you center them on the points of this point process. The next one is to look at a lattice, say ZD, the cubic lattice, but you can choose other lattices if you like. And I like to see this Japanese lattice that Bernard mentioned yesterday. Maybe I have a look at that too. So that's the famous periodic Lorentz gas. The other examples that I list here are ones that I studied with Andreas Strömbergsson in more recent work. So you could take unions of lattices that are incommensurable. I'll come back to that. Main point of my talk will be our recent work on quasicrystals. So you take the Penrose tiling, for instance. You play, and as a point set P, you take the vertices of this Penrose tiling, and you put your scatterers there. So that will be a quasicrystal scatterer configuration. And in the most recent work, we looked at polycrystals. I'll show you on the next slide what those are. And the point is that there's very little known for fixed radius. Most things that are known are in dimension 2 in the periodic Lorentz gas. And the point of my work is to go back actually to Lorentz's original idea and not fix the scattering radius, but shrink it to 0. This is the so-called Boltzmann-Grad limit, in which you can hope to see a macroscopic, non-trivial dynamics to emerge. So there is, in dynamical systems, you usually fix your dynamical system and you look at the long-time dynamics, the statistical properties that emerge. In kinetic theory, you are interested in the emergence of macroscopic phenomena, and this usually happens when you go into what Boltzmann would call a dilute gas limit. So the free path length, or the mean interaction time between particles, goes to infinity in that limit, and then you rescale time in such a way that you see, say, the Boltzmann equation, or in this case it would be the linear Boltzmann equation, emerge. So our point here is to not fix the radius, but shrink it with the scattering configuration fixed. Okay, so you fix your scatterer configuration P once and for all, and then you look at very, very small scatterers. And here is a polycrystal. So what is a polycrystal? These are the grains of the polycrystal, and each grain is basically a crystal, part of a crystal. So it's a lattice, and they're orientated in different ways. So this is what a polycrystal is. I'm not going to mention this at all anymore in the talk. There's a preprint up there on the rack, and I'm here, and we can all talk about it. But I want to focus sort of on the basic principle, and this gets a little technical, even though there are some nice features in this as well. So what I'm planning to talk about in this talk is just the pure crystal, which is a sort of older work, and then how this can be adapted to the case of quasicrystals. Okay, so here is just to fix things. We look at each scatterer, and each scatterer is supposed to be spherically symmetric, and the scattering map can be quite general. And just a fixed notation here, we have so this is your scatterer here, and if we have a particle coming in to our scatterer with velocity v in, it's going to be scattered in this way. B is called the impact parameter, theta is called the scattering angle, and S is the so-called exit parameter. And in a spherically symmetric configuration, just basically saying what the scattering angle is for a given B fixes your problem. And what we're assuming about our scattering map is very simple. So the theta, as I said, is a function of the impact parameter. And what we're assuming here is that it's strictly increasing or strictly decreasing one of these two situations. And these are, for instance, satisfied when you look at the classical hard sphere scattering, where your reflection law is simply that your incoming angle equals the outgoing angle, elastic reflection. In this case, you have this formula for the scattering angle in terms of the impact parameter. Or the so-called Muffin-Tin potential, Muffin-Tin Coulomb potentials, where you take a Coulomb potential and then you just truncate it, so you make it short range. We must, whatever we do here, we must have short range. would be beautiful to extend our things to infinite range potentials, even of some decay. So all our potentials have to have compact support for what I'm going to tell you to hold or to be provable. Well, that's the impact parameter. Probably I called it B before. I guess W will be just the absolute value of B. So B is a vector, but in the rotational symmetric potential, it's just enough to specify it on this section. Okay, so this is just the function of the impact parameter. And, well, so you have this as another example for which what I'm going to show you will hold. All right. So now, I said we need to shrink our scattering radius with a scatterer configuration fixed. And this is the so-called Boltzmann-Grad limit. Now, in order to see a macroscopic transport emerge, in the case when you shrink your scatterer, you have to think on how you will, and on which units you will measure your macroscopic effects. Okay, so it's clear that when you shrink your scatterer, that the time between collisions will grow. The smaller the scatterer, the longer your mean free path length. And you can calculate the mean free path length, and the mean free path length grows like r to the minus d minus 1. This is exactly the cross-section that you see when you are approaching a particle, right? So this is just the hyperdisk of dimension d minus 1 that your particle sees. That's the scattering, the total scattering cross-section of an individual scatterer. And one can show, and this is of course classic, that the mean free path length is exactly proportional to 1 over that cross-section. So this will be this quantity here. So this means you have to wait longer and longer until you hit something. So you rescale time by exactly these units. So now you'll hit again things on a sort of a macroscopic time scale. And similarly, you also would like to rescale space. Since you're flying longer and longer, it also means that the distance between collisions will grow at the same rate. So you also have to zoom out and rescale your length units in this way by the same factor. Remember, we're moving with unit speed. So I could have rescaled the velocity instead, but I've decided to keep velocity 1. Okay, so now this justifies the introduction of these macroscopic coordinates. And you could choose other coordinates if you like. So if you wouldn't rescale anything, you would get a trivial dynamics. You would never ever hit anything. Okay, so if you just decided, no, I don't want to rescale time, it's still fine, but then your initial particle cloud would move and would never hit anything because the scatterers are now so small and you're not waiting long enough. So this Boltzmann-Grad time and space scaling is the first scaling where we will see a non-trivial effect, as I'll indicate now. Okay, so the capital Q and V I will call macroscopic coordinates, and the little q and v will be my microscopic coordinates. Yeah? Yeah?
Probably silly question, but nonetheless. When you scale the space, you push the scatterers closer to each other.
That's right.
So, intuitively, time that one needs to, the time between the collisions becomes 1, of order 1, intuitively.
Intuitively, but of course you have to make a calculation. So you're right. So the picture in these macroscopic coordinates that you have in mind now is the following. This is your scatterer, and it will now have a radius which is, so initially the radius was r, but now we rescale the time units in this way, so it will now have radius r to the d, and the sort of average distance between our scatterers, which used to be 1 on the microscopic, on the original scale, will now on the macroscopic scale appear as r to the d minus 1. So we're pushing the scatterers together, but the scattering radius shrinks even faster on this scale. And then in this length scale, you would now hit points, if you move with constant velocity, with velocity 1, you would now hit particles on, as you say, on a constant time. So in this unit, you wouldn't have to rescale time anymore.
What bothers me a bit is that you do 2 rescalings. And as I said, it feels like you need to do only 1. Maybe I'm wrong.
So it depends what you start.
Another is length.
I can't hear you.
Dimension.
I can't hear you.
No, doesn't matter. He's wrong.
He's wrong and I'm right.
Yeah.
That's all I wanted to know. Okay, so you could set up, you could set up the problem in these units, but you have to remember that how velocity and time are related to each other. So, yeah, so it's, everything's consistent. Okay? Okay, so now in these units, we now start with a particle cloud, and we want it to be a macroscopic particle cloud, because we want to see that this thing moves in a nice fashion. So we start with a fixed function f in L1, and we transport it just by the classical Newtonian dynamics. That's our flow here. That's our billiard flow, if you would assume hard scatters, or Hamiltonian flow. And so we propagate that density in the standard way by evolving the argument backwards in time. So that's our density at time t, and it depends on the parameter r, which will be our small parameter. And in these units, in these macroscopic units, what Lorentz suggested is that indeed the evolved density for very small r is governed by the linear Boltzmann equation. I've written it down here. So the left-hand side is just linear transport without any scatterers. If you would set the right-hand side to 0 here, you would just move along straight lines. Okay, and so your particle density would evolve in the same way. And the right-hand side is the so-called collision integral, and that tells you that how your density changes in each collision. Okay, so that's the equation that Lorentz wrote down. It's called the linear Boltzmann equation. It's also sometimes called the kinetic Lorentz equation. And the quantity that appears here is the differential cross-section of an individual scatterer. And for example, when we have the specular reflection, it's an explicit formula and it looks like this. This equation has many applications: neutron transfer, radiative transfer. I've even seen a paper describing waves in the ocean scattered by little ice planks, which model the scatterers. So this is a very famous equation, and of course we could ask, well, can one make Lorentz heuristics rigorous? And Lorentz heuristics was really based completely on Boltzmann's argument and how he tried to derive the Boltzmann equation, which is of course still a major outstanding problem. And so he followed Boltzmann's Stoßzahlansatz and the classical argument to arrive at this equation. And it took over 60 years for Galavotti to make this rigorous under the assumption that the scatterer configuration is Poisson, given by a Poisson distribution. This was extended by Spohn to more general scatterer configurations and more general potentials than just the hard sphere potential, hard sphere scatterer. And finally, and these results were all convergence in probability. The ultimate result in this setting is by Boldrighini, Bonimovic, and Sinai, who fixed a realization of a Poisson process and proved that almost surely, for almost every realization of a Poisson scatterer configuration, you converge to the linear Boltzmann equation. In addition, you can ask the question in the quantum setting, and there has been quite a lot of beautiful work by Spohn, Erdős and Yao, Eng and Erdős on this question, how the corresponding quantum evolution converges in this Boltzmann-Grad limit, which is called here the low density limit, to the linear Boltzmann equation. Okay.
Which problem is harder, classical or quantum?
Classical.
Which problem is harder to solve?
Classical.
Shall we have a vote? Who thinks quantum is harder? Nobody. Who thinks classical is harder? 1, 2, 3, 4. So it's, I don't know. I've just started with a quantum problem in what I have here. The techniques are completely different. And this paper of Boldaghini, Bunimowicz-Sina is really beautiful, and it uses classical probability theory, beautiful estimates. While the work of Erdős and Eng, for example, on this problem is very hard Feynman type expansions and just keeping control of many terms. So it has a much more analytic flavor. And I don't want to judge what is harder or not. I think both are very, very beautiful contributions.
May I ask a
Yeah.
question? Do you understand correctly that with your space and time scaling, you have arranged so that the portion, the fraction of the time spent on the collision process as such is infinitesimal?
Yeah. It's,
So you get
yeah.
differential equation.
That's right. So, you know, so in the original setting, we fly for a very long time, and then the scattering takes a finite amount of time. Now I've rescaled time, so the scattering is now instantaneous, right? And you see this also in the linear Boltzmann equation. The scattering is instantaneous on the right-hand side. That's right. Okay, so what about non-random configurations? Here's the example of the periodic Lorentz gas. So the question now is, we start with a particle cloud, and the way I think of this is, rather than thinking of a particle cloud, I think of a single particle with a random initial condition, where the distribution of the initial condition is given by the density of your random cloud, right? So these are two equivalent pictures. So think of it this way. We start here with a random velocity, and we want to understand the distribution of this path, which is now a random path. Once we understand this random path, then we will also be able to derive the linear Boltzmann equation as the sort of Kolmogorov backward equation of this random process. And so the first question you ask yourself here is, how long do I fly until I hit the first scatterer? That's the so-called free path length distribution, right? If you want to understand the complete distribution of this path, first question is, when do you hit the first guy? And that's just the first leg of your journey. And there has been work by Bogin, Golze, and Van Berg, who proved that the distribution of free path length, so FRT is now, for a given radius r, is the probability that if I shoot off from a generic point in a random direction, what's the probability that I hit the first scatterer after time t? That's FR of t. There is a problem with the exponents. 2, t to the minus 2. In both cases, upper and lower bound. It's a notation is the problem.
People that don't like
Ah,
much less.
so this is defined, and I know this. I've been trained as a physicist, and I know physicists don't mean what I mean here.
There is a formal question. But if you look at the screen, you look at the left-hand side and the right-hand side,
Yeah?
and there is
They are
sign
identical.
much less than.
Yeah.
So for these two
And
things,
that's what I'm just explaining. Okay, so this means, and this means there exists a constant such that, so it doesn't mean much less, it just means less or equal up to a constant. Is everybody happy now?
No, because most of the people let's make a poll.
No, I don't need to make a poll because I know that's what it is, but it's a question of community. And this is a symbol that is used in number theory and some areas of analysis. So it's okay to use if I define it, right? Shall I put a little tilde over it? Would that make you happier? Okay, so this is what it means. So this means order of magnitude, okay? It just means order of magnitude is t to the minus 2. All right. Now, this is clearly different from the random scatterer configuration where the free path length distribution would be an exponential distribution. It's okay?
Yeah, it's unusual, but okay.
It's not unusual.
Usually is less sim. Usually is less sim.
Less what?
Less sim.
In harmonic analysis, they use this notation.
Yeah.
Less side and the wiggle below.
And you want a wiggle? No, I don't care. I've defined it, and this is a completely standard notation. And so you just have to live with it. Unless you want to write an essay, send it to me. What notation would be better? Okay, be happy to. No votes allowed. Another question?
Can I just use this confusion time? So I was confused now. Is it the what is random precisely? The position of your scatterers or the initial conditions?
No, the scatterers are fixed. We are in the periodic setting. The scatterers are completely fixed. They are on the periodic lattice points. And what is random is only the initial data. Okay, this is probably important to mention here. I'm not doing any disordered systems here. I'm really fixing my configuration to be periodic and later to be on a quasicrystal. And the only thing that's random is in the initial condition of my particle. That's the only random thing here, nothing else. Yeah? Okay. So, now in 2 dimensions, one can actually show, and this was done in a beautiful paper by Boca and Zaharescu in 2007, that the free path length distribution converges. So you don't just have upper and lower bounds, but you actually have a limit distribution, and they wrote down an explicit formula. Then in 2010, Andreas Strömbergsson and I generalized this to arbitrary dimensions. So we proved that the free path length distribution that appears here has a limit, okay? And so it has this density, and this density here actually has an asymptotics. So what this means is that now you don't need to worry anymore about upper and lower bounds because there is actually an asymptotic tail. So it is actually asymptotic to some constant c times t to the minus 2. Okay? This corresponds to the density, so goes like t to the minus 3, so the distribution function goes like t to the minus 2. And here is a plot of the distribution in 3 dimensions. You see it's a nice distribution, but it's a very non-standard distribution. It's not anything that we have seen before. And I'll show you why. The interesting feature here is, that was already clear of the work by Golzer, Bourgain, and Wenberg, is that this distribution doesn't have a second moment, and that will have an important consequence, namely that the diffusion process that you get here will be super diffusive, and I'll come back to that. Okay, so let's go back to so this answers the question of the free path lengths, but we wanted to know more. We actually wanted to know whether the dynamics of the particle cloud goes and converges to the linear Boltzmann equation.
With the free path length distribution, you don't do a rescaling, right? This is just sort of radius going to zero, but you don't do time rescaling. And
Everything's already rescaled here. So I'm already in the macroscopic units.
But didn't you say that you have instances and the instances
Scattering.
Scattering, yeah.
So we are now talking about the free path lengths, so the free flight time before we hit the scatterer. And I've chosen my units in such a way that this is now measured on the scale of the mean free path length. Okay? So we're flying for some constant, some finite amount of time, then we scatter more or less instantaneously. Okay? So it's that quantity. Okay, so this first theorem here establishes that, as before, so we just look at initial particle cloud driven by the Newtonian dynamics, Hamiltonian dynamics, that this has a limit, just as in the case of the random scatterer configuration. And this limit, so if we define here, if we define the evolution of our initial particle density by some semigroup of operators, LT, that's just defined in this way, this theorem says that this semigroup converges in a weak sense to a family of operators LT. And weak means simply here we take some nice test sets, we integrate our evolved particle density over this test set, and in the limit r to 0 it converges to this thing here. So it's a weak limit. And the interesting observation in this theorem is that the limiting family of operators does not form a semigroup, even though each, for fixed r, positive r, these guys form a semigroup, which is clear from here. And this is due to some loss of information. So what you need to do to recover the semigroup property, because remember, we would like to describe the evolved density by some integral partial differential equation. So we need a semigroup, and the way this can be recovered is by extending your phase space to a state space that doesn't only take into account q and v, position and velocity, but additional variables. And the right variables to choose here are the flight time until the next scatterer and the velocity after the next scatterer. Now, in the microscopic Hamiltonian dynamics, of course, psi and v plus are functions of q and v, right? Q and v determine everything until the future. But what happens in this weak limit is that these variables become independent from q and v. Independent in a not in the sense of independent random variables, because they'll still be connected, but independent as deterministic functions of q and v. And if you now extend your state space in this way, and you now consider densities that don't only involve qv but also psi and v plus, you can show that you have a weak convergence to a limit density ft in these four variables, and that this evolved density satisfies now what we call a generalized Boltzmann equation. And so again, on the left-hand side, you have a linear transport term. You have the additional minus d by d psi here, because the time until the next scatterer, of course, decreases. So time increases, this decreases. So this explains this term here. And then you have a more complicated collision integral that doesn't only take into account the differential cross-section of each scatterer as in the linear Boltzmann equation, but a more complicated transition kernel that also depends on these new variables psi and v plus. So this is our new generalized linear Boltzmann equation. And okay, so the original question of how does our particle density evolve is simply then obtained by integrating out those additional variables. So phi t is now generated, and the 4 variables now generated by a semigroup of operators, and this projection here simply doesn't commute in general with this semigroup, and that's why phi t bar is not generated by a semigroup. Okay. And you get in particularly a physical problem if you choose a very specific initial condition here for your generalized Boltzmann equation, which is your initial particle density times the stationary solution of the generalized Boltzmann equation. So that's the situation, that's the result. And you can now ask, for example, what happens with our solution of the generalized linear Boltzmann equation, which describes the dynamics of our particle cloud in the periodic Lorentz gas in this Boltzmann-Grotz scaling limit. What happens for that for long times? So this is now getting a little complicated. We have already rescaled time to be measured in units of the mean collision time, and now we're asking what happens when we pass to the limit when this time is large compared to the mean collision time. And in joint work with Ball and Todt, what we prove is that you can have, or that in this case, you have a super diffusive central limit theorem. So we take our initial particle position Q naught, and we shoot off from a random Q naught with a random velocity V naught, and we assume it's distributed according to some absolutely continuous measure. So that just means we have a L1 particle density, okay? And we just ask now, for the distribution of the displacement at time t. So we observe where the particle is at time t in the macroscopic coordinates. We rescale everything by square root t log t. That's why it's called super diffusive. And then you can prove this central limit theorem. I'm not going to talk about the proof of this. It involves proving a new central limit theorem for a certain class of Markov processes. And the reason why we see this super diffusion is precisely because the second moment diverges. So we are exactly in this non-standard domain of attraction of the central limit theorem. And what is new here is that this is the first result for the periodic Lorentz gas in dimensions greater than 2. So previous results concern the case when you fix the radius, but all that is known there is the two-dimensional case, and there are some serious technical obstructions on how to extend this to higher dimensions. And so what is nice to see here, that if you assume that your scatterers are small, your time is large. So the order of the limits here is absolutely crucial, is that you see the super diffusion in any dimensions, because that's also not a completely obvious thing, right? You could have, in higher dimensions, you could have a different normalization, not by square root t log t, but maybe by a power. You could see maybe there's a Levy flight. Now, the plan for the remaining 15 minutes of this talk is to give you an impression on how we establish the first theorem on the existence of a macroscopic limiting process. And I'm going to focus on this, on explaining to you the distribution of the free path lengths. But just to say, the theorem A, the convergence of this, the weak convergence of the propagated particle density follows from a more general theorem on the convergence of this process here. So this is a random process, yeah? So it means we start with a random initial condition, and that gives us a random trajectory. But it is a very deterministic random process, because the only randomness is in the initial condition. Everything else is determined. It's still a random process. It's not a random walk with independent increments, but it's still a random process. And we want to show that this random process converges to another random process. So And you could call this a random flight process because you always fly for some time and then your velocity jumps, and then you fly again and your velocity jumps. Or you could call it a jump process, I guess. So this is really the key theorem that we have here, and that's a theorem that tells you that the joint distribution of these legs of your flight process for every fixed n, so you look at the first n legs, that has a limit distribution. And as you see here, this limit distribution is given by a Markov chain with memory 3. Okay, so the left-hand side is your actual path segments, where the only randomness is in the initial condition, Q0, V0, and this theorem says that this converges to a joint distribution of the first n path segments, and this the limiting density factorizes in this way, so you see here a Markov chain appearing. And the key fact, which saves everything, is that this has memory 3. In the random configuration of scatterers, it would just be memory 2. So we have an additional memory effect here, which means that we need to increase our state space. And so this is the basic, the key theorem. Okay, so now how do we prove a theorem of this type? Well, let's just focus on the case n equal 1, and that's the distribution of free path lengths. Right, because S1, velocity is determined for the first just by V0, so it's really just the length of the first leg, and that's just the free path length. So here's how the proof works. So we introduce not just the lattice we start off with, but a whole space of lattices, and you can do this by starting with your cubic lattice ZD, and then you apply linear volume preserving transformations from the group SLDR, just D by D matrices with determinant 1. You realize that there is a subgroup in here, the so-called modular group, which preserves your initial cubic lattice. And so what one can show is that you can parametrize the space of such lattices by this quotient space, SLDR modulo SLDZ. That's a homogeneous space. And the beautiful thing, which was Minkowski who pointed that out first, is that this space carries a probability measure that is invariant under SLDR. That's just the Haar measure on this Lie group projected on here. It's finite, so you can normalize it. It's a very non-trivial fact, and that means we can now talk about a random lattice. Right? What does it mean? We just pick a point in here with respect to this Haar probability measure, and that point in here will give rise to a matrix M, and therefore to a lattice here. So now we have a notion of a random lattice. Why do we need this? Okay, there's also a notion of a random affine lattice if you also allow for translations. But ignore that, okay? Well, if you've never seen this before. So instead of fixing a lattice which is sort of centered at the origin, you can also translate that lattice, right? And so you can also talk about a random affine lattices by simply translating your initial point randomly on the unit torus. Right, so now I want to explain to you this first theorem on the distribution of free path lengths. So I first want to state it, and it says the following. So we fix some initial points. So I'm actually now doing something slightly more difficult. I'm not going to take my initial point to be random, but I fix it. And now the only random thing is now the initial velocity. And I'm doing this for a reason, because I want to explain to you exactly how this kind of proof works, and it's a little bit clearer if we actually fix the initial velocity. Plus we get some interesting observation. And so this is the following. So this theorem says, well, so tau 1 is now the distribution of free path lengths measured in the raw units. So I need to rescale by r to the d minus 1 as before, okay? So so we're asking here, what's the probability, i.e. what's the measure of directions so that my trajectory doesn't hit a scatterer after time, hasn't yet hit a scatterer at time xi. So this theorem says that the distribution exists and is given by the following formula. Okay, so this is the limiting distribution, and you see here it depends whether your initial point is on the lattice or whether it is generic. And generic just means here it's not a rational multiple of a lattice vector. So this lambda naught, just take it to be ZD. Okay, so lambda, not lambda, sorry, L naught here is just ZD, if you like. We can do it for any lattice, but this is already difficult enough. And we have chosen some probability measure on the directions. You can just take this to be the uniform measure on the sphere. Problem is already hard enough. So it's not here a point of having lambda absolutely continuous, and it's already, if lambda is a uniform measure, this theorem is already difficult. So what's the limiting distribution for the free path lengths? It's the probability, if Q is on a lattice point, it's the probability that a random lattice doesn't intersect a certain cylinder. And I've written down here, it's a standard cylinder. And if you are shooting off from a generic point, the limit distribution is given by the probability that a random affine lattice doesn't intersect a cylinder. So what you see here is that indeed the Diophantine conditions on the initial point come in, but just as in Svetlana's talk, what we're very proud of here is that we don't need a Diophantine condition except to say we're a lattice point or we're irrational. Our theorem, by the way, also holds when Q is a rational multiple of a lattice point, but I haven't written this down here because the limit distribution is more complicated. So we get an answer for every lattice point. And we're very proud of this because even in 2 dimensions, this is a completely new result. Whenever you, so only when you start from a lattice point, that was known by Boca and Zaharescu. Everything else is new. Okay, here's how the proof goes. And I'm just going to show you the key argument. So we are interested in the probability that a certain ray doesn't intersect of length psi, rescaled in this way, doesn't intersect a scatterer. So this would be a bad one, so this would not be part of this measure. Okay, so what we do is we understand that this is actually the same as not having a lattice point in the cylinder. Okay, the two things are dual. You need to just take care here that you really want a cylinder with caps, but let's ignore that technical subtlety because it's going to be a very small thing. Remember that the cylinder in the original microscopic coordinates is very long. It has length r to the minus d minus 1. That's the mean free path length, and our scatterers have radius r, so this is a long stretched cylinder. What we're going to do now is we apply a linear volume preserving transformation, namely a rotation, to get it into this form. And then the next thing we're going to do is we're going to stretch, apply another volume preserving transformation that just pushes everything together. And then you see what happened to our cylinder is that it now is no longer thin and it's no longer long. Okay? It has a nice fixed size, which now is r independent. But the trade-off is that we've applied those linear transformation to our lattice. And this means that we are moving through the space of lattices. And the rotation that we apply here was a random rotation because my initial direction was random, right? I'm asking for the measure of V's. In other words, I'm asking for the probability that a certain V intersects or doesn't intersect this thing, right? So that's random. So the trade-off now is that we are here asking what is the probability that a randomly rotated and stretched lattice doesn't intersect the cylinder. And in order to answer this question, we apply very sophisticated techniques from ergodic theory on the about the dynamics on the space of lattices, and in particular we apply mixing properties, but in the more sort of subtle questions, Ratner's classification, measure classification theorem. So the key idea here is that once you understand that a randomly rotated and stretched lattice in the space of lattices converges in distribution to a random lattice, you're done. Okay, that's the key idea of this proof. And there are, of course, many technical subtleties you need to understand, but that's the main idea. All right. So I hope I've given you some flavor of what happens in the periodic setting. So now how about other scatterer configurations like quasicrystals? So let's just talk generally here. So we start with a point set on which we want to locate our scatterers, and let's just assume it has unit density, by which I mean counting the number of points in a big ball will be asymptotic to the volume of that ball. And then you say, well, now instead of looking at a randomly rotated lattice as before, I'm now looking at a randomly rotated point set, right? So you can ask exactly the same question. Now, this matrix KV is our random rotation, and dr was the stretching matrix. So we randomly rotate and then we stretch. So this is a random point process. P is a fixed set. It's randomly rotated, so that gives rise to a random point process. And then you stretch this thing by this matrix dr, and you're interested in the limit as r tends to 0. So you get a sequence of random point processes. And what you really want to understand is whether the sequence of random point processes has a limit as r tends to 0. That's really the key question in probabilistic language. Okay, and so of course you can ask this question, very natural question to ask here. But of course it's very tricky because you just start with some fixed point set and you need to first understand in which probability space it lives and whether there is a natural limit to which it could converge. So we can't do this in generality, and so we go step by step now. And so I'm going to present you the 2 case studies that we've carried out, and the third one is up on the shelf, the polycrystals, as I mentioned. Okay, first case study is you take a union of lattices. So you just take your initial lattice ZD and just take another ZD, but just rotate it against the first ZD, right? And you ask the same question as before. So what we can show, again using this ergodic theoretic machinery, is that the limiting random point process that we now get is provided one lattice is rotated generically against the other, not randomly rotated against the other, but generically, so by some irrational angle, say, that in the limit, these two guys will become independent. So the limiting distribution will now be given by the probability that we don't a random lattice doesn't intersect our favorite cylinder times the probability that the other random lattice doesn't intersect that cylinder. The two will become independent. That's what we prove. That's of course a decorrelation result, okay? The other case study that we have here, and I invite you to look at this paper, and and the interesting observation or consequence of this independence is that now the distribution of free path lengths can have any power law decay if n is the number of lattices you superimpose. So n was 1 in the periodic setting. If you take n lattices and they're generic with respect to each other, you get this kind of power law decay in the limit. So that's an interesting observation. Okay, now in the case of quasicrystals, we start, for example, with a Penrose tiling. We put at each vertex a scatterer, and we ask the same question as before. Do we get a generalized linear Boltzmann equation? Do we have a limit distribution for the free path lengths? And we've worked this out in quite some generality, where we look at quasicrystals that arise as so-called cut and project sets. So what you do is you start with a higher dimensional lattice. So suppose you want to construct a cut and project set or a quasicrystal in 2 dimensions, like the Penrose tiling. You take a lattice in, say, 5 dimensions, as you would do for the Penrose tiling, and you then define a certain window set, and you take all lattice points in your 5-dimensional lattice that project orthogonally into that window set. You take all those points and project them down into your 2-dimensional physical plane. That's a standard construction. And if we have such a construction, so I've written it down here. So you basically define W to be a window set in your internal, your auxiliary space, Rm here, and then you take all lattice points, y in L, that project into this window set, okay? And you take all those lattice points and you project them onto your physical space RD. This is called a cut and project set. And what we prove then is that for all such constructions under certain regularity assumptions, again, the distribution of free path length exists. And just exactly in analogy with what I've showed you before in the periodic setting, we now define not a space of random lattices, but a space of random quasicrystals that defines the limiting distribution. But it would lead too far to explain this in the last few minutes. The key observation is that we now use a more sophisticated equidistribution theorem on the space of lattices, which is still sitting in the background. So even though you see a quasicrystal there, in the background is this high-dimensional lattice. But now we're not rotating this high-dimensional lattices in all possible directions with respect to an absolutely continuous measure. We are only rotating it in our physical direction. So in the case of the Penrose tiling, our lattice is 5-dimensional. Penrose tiling lives in 2 dimensions. But in order to understand the free path lengths, we only vary the initial velocity in this 2-dimensional plane. Okay, so we're now averaging in the space of 5-dimensional lattices along a 2-dimensional rotation. And we can still show that this average becomes uniformly distributed in a suitable subspace in the space of lattices. Does that make sense? That's sort of the philosophy of what we're doing, but we need more and more sophisticated equidistribution problems. You appreciate that rotating it over the full space, you know, is a much thicker average than rotating over a very thin slice in that space. And this is what makes this more subtle here. I've put 2 examples down, but I don't think I want to go through it. The only message is we can deal with the Penrose tiling, and the exciting observation that we have is that rather than becoming equidistributed in the full high-dimensional space of lattices, we become equidistributed in a subspace which is related to so-called Hilbert modular surfaces. I'm happy to talk to anybody about this who is interested in this special feature, but I think my time's up. So just remains to give you the take-home message, which is in the Boltzmann-Grad limit, you can see much, much richer Boltzmann equations emerge than those originally proposed by Lorentz, this generalized linear Boltzmann equation. And they, in a very subtle way, depend on the arithmetic of the point set that you consider, be it periodic, quasicrystal, unis of crystal, or the polycrystals that we've looked at. The key point in proving anything here is to understand the distribution of expanding spheres in the correct moduli spaces. Thank you.
So when you then kind of look at the path and you converge, I mean, from this, except for the initial condition, from this trajectory to a random process, which is sort of Marklof, then it means you somehow have some memory loss where you came from.
Yeah.
So is it easy to understand somehow where this memory loss comes from in this limit?
Yeah, so it's something you need to prove, but the intuitive meaning, what you need to, the key point of what you need to prove in this is the following. So what you consider is the scenario when you've just hit a scatterer. So you've just hit a scatterer. So you came from somewhere, you've hit the scatterer, and then you are moving to the next scatterer. So usually, because scatterers are very far apart, you can assume that when you hit a scatterer, with one trajectory, there will be a small neighborhood of trajectories that also hit the scatterer that have the same history. It'll be very, very small, tiny proportion, but remember our scatterer is also very tiny, okay? So you hit this thing, and so now this will induce a probability distribution on the outgoing velocities. Okay, so now we will hit this, and with each guy you will get a different outgoing velocity. And so the outgoing velocity here will be a random variable that depends on the history. But it will not depend on the history too much, because essentially all these guys come in parallel. Okay? Not quite parallel, so there will be some dependence on your little parameter r, but you can assume that the distribution, the measure on the outgoing velocities here, depends on r, but not too much. Okay? So you just ignore that for the sake of argument. And then the key point in our proof is that the probability of hitting the next scatterer actually doesn't depend on the choice of this measure lambda at all, okay? Except, so the only things that are relevant here is the exit parameter and the impact parameter to understand what is the flight time. Does that make sense? So this is the key point, that the limit, and you've seen this in the distribution of free path lengths, I didn't highlight it in the talk, but no matter what lambda I chose for the distribution of free path lengths, the answer was independent of lambda. And this also happens here in this setting. And that is why you do get memory loss. So when you look at these expanding spheres, it doesn't matter if you take the uniform measure or just a little patch. They will converge to the same limiting measure.
Are there more questions?
So you had a colorful picture like a single point and then three different directions,
Yes.
three colors, and then you study distribution. Means that you have completely random initial conditions, right? But if you say, if you looked at, okay, there is a position and velocity, right? Initial position and initial velocity. But if you try to separate them, say, initial position is random, but velocity is not. Meaning in the sense that you assign some initial direction. Will this tendency to move in that direction be eventually lost? Or
No. So if we only take q to be random and fix the velocity v, we can show that we only converge along subsequences, but the limit will not exist. So there is a clear distinction, for instance, if you go in a rational direction or irrational direction. But even if you go in an irrational and generic direction, the limit will not exist. You will have to perform an extra Cesaro average. And if you like, the reason for this, in some sense, is the velocity v that you can think of here is like an alpha in a continued fraction expansion. And if alpha is generic, your continued fraction expansion will not stabilize. It will be something. And this is exactly sort of this phenomenon that happens here in this periodic setting.
And I ask you during the talk, which of the two is harder, classical or quantum? You said that it's a completely separate story. But one could imagine that if your motivation is classical and suddenly quantum is a little bit easier, then you could use it as a kind of tool for addressing eventually a classical problem, like a kind of regularization, passing to the limit. Is it not?
So here's my answer now to your question. In the quantum setting, the problem is more varied because you also have the wavelengths to consider as a scaling parameter. If you look at the scaling limit where the wavelength is very small compared to your scatterer, you're in the semi-classical scattering regime. And in this case, I'm hoping that you will recover effects like this. But it will be harder because you have an additional phase factor to consider. If your wavelength is comparable or even bigger than the scattering size, I believe the thing will become easier. And I even believe now that you will lose all these effects. You will actually, that's my conjecture, converge to the linear Boltzmann equation, quantum linear Boltzmann. Yeah, I'm hoping that that's why I'm here, and that's why I'm talking to you guys. That homogenization techniques might help, or other techniques. So I think It can be sometimes harder, it can be sometimes simpler, because you have more scaling limits to consider here.
Okay, some more questions? Let's thank the speaker again.